Section 1.9, Exponential and Logarithm Equations. In this section, we'll take a look at solving equations with exponential functions or logarithms in them. We'll start with equations that involve exponential functions. The main property that we'll need for these equations is the log of base b of b to the x, which is equal to x, which means that the exponent on base b to get b to the x is equal to x. Now for example 1, we're going to solve 7 plus 15 e to the 1 minus 3z is equal to 10. Now the first step is to get the exponential all by itself on one side of the equation with a coefficient of 1. So the variable is in the exponent of e. So we want to isolate the base of e. So the first thing we're going to do is we subtract 7 to both sides. So 10 minus 7 is 3. And then we're going to divide by 15. So now we have e to the 1 minus 3z, which is equal to 1/5. Now we need to get the z out of the exponent so that we can solve for it. To do this, we will use the property above. Since we have an e in the equation, we'll use the natural logarithm. So first we take the logarithm of both sides and then use the property to simplify the equation. So we have the natural log of e to the 1 minus 3z, which is equal to the natural log of 1/5. Now because the base is e here and this is e, then now we can get the variable z out of the exponent. So we have 1 minus 3z, which is equal to the natural log of 1/5. Now all we need to do now is solve this equation for z. So what we're going to do is we're going to subtract 1 to both sides, so we get negative 3z, which is equal to negative 1, plus the natural log of 1/5. And then we're going to divide everything by 3. So we can divide everything by 3, or we can just rewrite this as negative 1/3 times negative 1 plus the natural log of 1/5, which gives us the following decimal, which is 0.8698126372. Example 2, we're going to solve 10 to the t squared minus t, which is equal to 100. Now, in this case, it looks like the best logarithm to use is the common logarithm. Since the left-hand side has a base of 10, there's no initial simplification to do, so just take the log of both sides and simplify. So we're going to take the log of the left side, which is log of 10t squared minus t, which is equal to the log of 100. Well, the log of 100 is log of 10 to the second power, which we know is 2. So that means that since we know that this equals 2, and what I mean by that is that we know that this results into 2, and then simplifying this logarithm here, since the common logarithm has a base of 10 and this is 10, so we bring down the exponent, which is t squared minus t, which is equal to 2. So at this point, we've just got a quadratic that can be solved. So we're going to subtract 2 to both sides, and so we get t squared minus t minus 2, which is equal to 0. And then factor, we get t minus 2 times t plus 1 is equal to 0. So it looks like the solutions in this case are t is equal to 2 and t is equal to negative 1. Now that we've seen a couple of equations where the variable only appears in the exponent, we need to see an example with the variables both in the exponent and out of it. So for example 3, we're going to solve x minus x raised to the power of 5x plus 2 is equal to 0. Now the first step is to factor an x out of both terms. Here's one term, here's the second term. Do not divide an x from both terms. Note that it is very tempting to simplify the equation by dividing an x out of the both terms. However, if you do that, you'll miss a solution, as we'll see. So we're going to factor out an x, and then we get x times 1 minus e to the power of 5x plus 2, which is equal to 0. So it's now a little easier to deal with. So from this, we can see that the 0 part rule tells us that we get one of the two possibilities. We know that x is going to equal 0 is one solution, and the other one is 1 minus e to the 5x plus 2 is equal to 0. Now we already know that x is equal to 0, so the first possibility has nothing more to do, except notice that if we had divided both sides by an x, we would have missed this one. In the second possibility, we've got to do a little more. So this is an equation similar to the first two that we did in this section. So we have e to the 5x plus 2 is equal to 1. So if we take the natural log of both sides, we get 5x plus 2 is equal to the natural log of 1. And now we need to solve for x. But now keep in mind that the natural log of 1 is equal to 0. And now we need to solve for x by subtracting 2 and then dividing it by 5. So x is going to equal negative 2 over 5. Don't forget that the natural log of 1 is equal to 0. So the two solutions are x is equal to 0 and x is equal to negative 2/5. Now the next equation is a little more complicated, but just looking at least, example similar to the previous one. So for example, we want to solve 5 times x squared minus 4, which is equal to x squared minus 4 e to the 7 minus x. As with the previous problem, do not divide an x squared minus 4 out of both sides. Again, doing this will lose solutions even if it simplifies the equation. Note, however, that if you can divide a term out, then you can also factor out of the equation if it's written properly. So the first step here is to move everything to one side of the equation and then factor out x squared minus 4. So we're going to subtract this term on the right side of the equation and bring it to the left side. So we have 5 times x squared minus 4 minus x squared minus 4 e to the 7 minus x. And now we can factor out the x squared minus 4. So if we factor out the x squared minus 4, then what's remaining is 5 minus e to the 7 minus x, which is equal to 0. So now we have two things that we can set equal to 0. So using the zero product rule, x squared minus 4 is equal to 0. And if we add 4 to both sides and take the square root, that means we get two solutions. X is equal to plus or minus 2. On this side, we are going to subtract 5 to both sides and then divide both sides by a negative to get e to the 7 minus x, which is equal to 5. Then we're going to take the natural log of both sides. When we take the natural log of both sides, we end up with 7 minus x, which is equal to the natural log of 5. And then we're going to subtract 7 and then divide by negative 1. So x is going to equal 7 minus the natural log of 5, which gives us the following decimal. So there are three solutions. We know that x is equal to plus or minus 2, and x is equal to 5.3906. Now, as a final example, let's take a look at an equation that contains two different exponentials. We're going to solve 4e to the 1 plus 3x minus 9e to the 5 minus 2x, which is equal to 0. The first step here is to get one exponential on each side, and then we'll divide both sides by one of them, which doesn't matter for the most part. So we'll have a quotient of two exponentials. The quotient can then be simplified, and we'll finally get both coefficients on the other side. Doing all this gives us the following. So, if, going back to what the equation is read here, what we're going to do is we're going to add 9e to the 5 minus 2x to the right side of the equation. So that's what we get over here. And now what we're going to do is we're going to divide the right side by 4. So we're dividing both sides by 4, and then we're dividing both sides by e to the 5 minus 2x. What this does is this allows us to use the exponent rules. Okay, so on the right hand side we got 9/4, we can leave that alone. So if we have the same base and we're dividing them, that means we need to subtract the exponents. So it becomes 1 plus 3x minus 5 minus 2x. So if we distribute the negative sign and combine like terms, now we end up getting e to the 5x minus 4, which is equal to 9/4. Note that while we said that it doesn't really matter which exponential we divide out by doing it, the way we did here will avoid a negative coefficient on the x. Not a major issue, but again, those minus signs on coefficients are really easy to lose on occasion. This is now in a form that we can deal with, so here's the rest of the solution. E to the 5x minus 4 is equal to 9/4. If we take the natural log of both sides, we get 5x minus 4, which is equal to the natural log of 9/4. Add 4 to both sides and then divide by 5. X is equal to 1/5 times 4 plus the natural log of 9/4. And so this equation has a single solution of x, which is equal to 0.9622. Now let's take a look at some equations that involve logarithms. The main property that we'll be using to solve these kinds of equations is b to the power of the common logarithm of bx, which is equal to x. So here we want to solve 3 plus 2 times the natural log of x over 7 plus 3, which is equal to -4. The first step in this problem is to get the logarithm by itself on one side of the equation with a coefficient of 1. So the first thing we're going to do is subtract 3 to both sides, so we get -7 on the right-hand side. And then we're going to divide by 2. So now we have the natural log of x over 7 plus 3, which is equal to -7 over 2. Now, we need to get the x out of the logarithm, and the best way to do that is to exponentiate both sides using e. So in other words, we're going to have e to the power of the natural log of x over 7 plus 3, which is equal to e to the power of -7 over 2. So using the property above with e, since there is a natural logarithm equation, if we use that, then what's left now is just x over 7 plus 3, which is equal to e to the -7 over 2. So now in this equation, all that we need to do now is solve for the value of x. So the first thing we need to do is subtract 3 to both sides. So we have x over 7, which is equal to -3 plus e to the -7 over 2. And then we're going to multiply both sides by 7, so we get x, which is equal to 7 times -3 plus e to the -7 over 2, which is equal to -20.7886182. Now at this point, we might be tempted to say that we're done and move on. However, we do need to be careful. Recall from the previous section that we can't plug a negative number into a logarithm. This by itself doesn't mean that our answer won't work since it's negative. What we need to do is plug it into the logarithm and make sure that x over 7 plus 3 will not be negative. I will leave it to you to verify that this is in fact positive upon plugging in our solution into the logarithm, so x is equal to -20.7886182 is a solution to the equation. Now, let's take a look at a more complicated equation. Often there will be more than one logarithm in the equation. When this happens, we will need to use one or more of the following properties to combine all the logarithms into one single logarithm. Once this has been done, we can proceed as we did in the previous example. Recall that the log of base b of xy, the multiplication expands into addition. The division here turns into subtraction, and then the power rule property, the r now becomes multiplied by the logarithm. So for example 7, we're going to solve 2 times the natural log of the square root of x minus the natural log of 1 minus x, which is equal to 2. So first, we get the two logarithms combined into a single logarithm. So recall here that we have this 2 in front of the logarithm. So we have to use this property up here to rewrite the 2 as an exponent of the square root of x. So we have the natural log of the square root of x squared minus the natural log of 1 minus x, which is equal to 2. Now, when we square a square root of x, what's left is just x. So now we have the natural log of x minus the natural log of 1 minus x, which is equal to 2. Now, since we have a minus here, we're now going to use the subtraction property to turn it into division. So it becomes the natural log of x divided by 1 minus x, which is equal to 2. And now what we're going to do is we're going to exponentiate both sides and solve for x. So if we set, and let's just go ahead, I'm going to write this over here. So what that means is when we exponentiate, recall that this becomes e to the natural log of x over 1 minus x, and that's going to equal e squared. And so then from here, that becomes x over 1 minus x, which is equal to e squared. And now we want to solve for x. So the first thing we want to do is multiply both sides by 1 minus x. So we get x, which is equal to e squared times 1 minus x. And then we distribute the e squared to both sides, to both terms. So we get x, which is equal to e squared minus e squared x. Now since we want to solve for x, we're going to add this e squared to the x to the left side and then factor out the x. So when we do that, we factor out the x, and what's left is x times 1 plus e squared, which is equal to e squared, and then divide by 1 plus e squared. So x is going to equal e squared over 1 plus e squared, which gives us that answer. Now the solution work here was a little messy, but this is work that you will need to be able to do on occasion, so make sure that you can do it. Finally, we just need to make sure that the solution x, which is equal to the 0.88079070, doesn't produce negative numbers in both of the original logarithms. It doesn't, so this is in fact our solution to this problem. But don't forget to check to make sure that it doesn't. Now let's take a look at another example. Example 8. We want to solve the log of x plus the log of x minus 3 is equal to 1. Now, as with the last example, we can combine the logarithms into a single logarithm. Since this is addition, then we can rewrite this as a single logarithm with multiplication. So this becomes a log of x times x minus 3, which is equal to 1. Now remember that this is a base of 10, so we're going to exponentiate using 10 this time instead of e, because we've got common logarithms in the equation on both sides. So we're going to get 10 to the log of distributing the x of x squared minus 3x, and over here we're going to have 10 to the first power. So now this becomes x squared minus 3x, which is equal to 10. Subtract 10 to both sides, set it equal to 0, and then factor. We get x minus 5 times x plus 2, which is equal to 0. So the potential solutions are x is equal to 5 and x is equal to negative 2. Now note, however, that if we plug x equals negative 2 into either of the two original logarithms, we would get negative numbers, so this can't be a solution. We can, however, use x is equal to 5. So again, if we plug in negative 2, we can't find those logarithms, so 5 is a solution. So therefore, the solution to this equation is x equals 5. Now, when solving equations with logarithms, it is important to check your potential solutions to make sure that they don't generate logarithms of negative numbers or 0. It is also important to make sure that you do the checks in the original equation. If you check them in the second logarithm above, after we've combined the two logs, both solutions will appear to work. This is because in combining the two logarithms, we've actually changed the problem. In fact, it is this change that introduces the extra solution that we couldn't use. Also, be careful in solving equations containing logarithms. Do not get locked into the idea that you will get two potential solutions and only one of these will work. It is possible to have problems where both are solutions and where neither are solutions. So there's one more problem that we should work with. Solve the natural log of x minus 2 plus the natural log of x plus 1, which is equal to 2. So the first step of this problem is the same as we've been doing up to this point. So let's combine the logarithms. So since it's addition, we're going to multiply these two together. So we get x minus 2 times x plus 2, x plus 1, which gives us a natural log of x squared minus x minus 2, which is equal to 2. And now we can exponentiate both sides with respect to e to eliminate the natural logarithm. Doing this along with a little simplification gives us x squared minus x minus 2, which is equal to e to the second power. And now what we're going to want to do is we want to subtract the e to the second power and set it equal to 0. So we've reached to the point of this problem. We need to solve this quadratic, and without the e squared, everyone would be able to do that. However, with the e squared, people tend to decide that they can't do it. This is just a quadratic equation, and everyone in this class should be able to solve that. The only difference between this quadratic equation and those you are probably used to seeing is that there are numbers in it that are not integers, or at worst, fractions. In this case, the constant in the quadratic is -2 minus e squared. And so all we need to do is use the quadratic formula to get the solutions. So the solutions to the quadratic are the following. So let's just let me repeat here. If we're going to use the quadratic formula, the value of A is going to equal 1. The value of B is going to equal -1. And the value of C is going to equal -2 minus e squared. So when we plug it into our quadratic formula, we get 1 plus or minus the square root of 1 minus 4 times 1 times -2 minus e squared over 2, which simplifies to 1 plus or minus the square root of 9 plus 4e squared over 2, which gives us -2.6047 and 3.6047. So do not get excited about the messy solutions to this quadratic. We will get these kinds of solutions on occasion. The last step to this problem is to check the two solutions to the quadratic equation in the original equation. Doing that, we can see that the first solution, -2.6047, will give negative numbers in the logarithms, and so it can't be a solution. On the other hand, the second solution, 3.6047, does not give negative numbers in the logarithms, and so it's okay. So the solution to the original equation is x, which is equal to 3.647.